So today we're very happy to have Hsiang-Chih to give us a seminar on binaries. Well, we know Hsiang-Chih very well. He got his PhD last year from Johns Hopkins University, working with media. So today he's talking about not your grandparents' binary stars. I wonder what does it mean. So go ahead, Hsiang-Chih.
Thank you for the introduction. So hello everyone, I'm Hsiang-Chih Hwang. So today I want to talk about not your grandparents' binary stars. The reason I say not your grandparents' binary stars is because binary stars is actually very, very old topics in astronomy. Actually, like back to ancient Egyptians' time, they already know some binary star, especially from like eclipsing binary. And far before we know this Newtonian gravity. Yeah, so yeah, binary star is a very, very old topic. So that's why I give it the topic, the title that not your grandparents' binary star, because right now we actually, especially in this decade, we understand it much, much more. So not anymore like that's what you thought. So okay, so yeah, binaries is probably one of the oldest topics in astronomy. Then why do we still care about binary stars? So first of all, it's because they're almost everywhere. So for example, our solar system, thankfully our solar system is a single star system. Otherwise, if our sun is in a binary system, probably we human beings may not even exist. So yes, so thankfully our sun is a single system. And the brightest star in the night sky, Sirius, is in fact a binary system. So this is the Hubble Space Telescope image of Sirius. And you can see actually a very, very tiny dot nearby it. And it's actually its white dwarf companion. So yes, the Sirius actually have a white dwarf companion. And the star closest to our sun, Alpha and Proxima Centauri, is in fact a triple system. So to put it in a more statistical way, about 50% of the solar sun-like stars are in multi-object system, including binary star and triple star and higher order multiples. And this fraction becomes higher and higher, like almost 100% for more massive stars. And therefore, because these binary systems are almost everywhere, they actually are a critical ingredient in star formation and evolution. Okay, and the closed binaries are actually the origin of a lot of extraordinary events in the universe. So kilonovae are coming from the merger of double neutron stars, and type Y supernovae, they are from binaries with white dwarfs. And there are also a lot of different kind of stellar mergers that we haven't fully understood yet. So therefore, understanding these evolution of these closed binaries and their formation actually help us to know much more about their progenitors and also the properties of these explosions. And on the other extremes, why do we care about Y binaries? So for Y binaries, it means that their separation are so wide, so that at that point, they are weakly bound. And because they are weakly bound, now, if you have any perturbation like passing star or any something else, molecular clouds, spiral arms, or anything like invisible, that can actually disrupt your Y binaries. And therefore, Y binaries actually is a very unique probe for us to understand the gravitational field on about 1 parsec scale. And so, for example, back in the day, people were asking, can dark matter be something like black holes or neutron stars? So you can see them, but they still contribute gravity. And if that's the case, based on the the dark matter profile, they can estimate how many black holes and neutron stars we need to match that profile. And if in the end they found that they need a lot of black holes in the dark matter halos. And if that's true, then that actually will disrupt all the Y binaries in the Milky Way halo. And therefore, back in the day, people used these, they found sufficient number of halo Y binaries so that they can say that, okay, so because we see these Y binaries are still in the Milky Way halo, it means that we don't have that many compact objects in the Milky Way halo. And therefore, we can rule out that no, dark matter is not just black holes and neutron stars. Okay, so that's one classical example for how we can use Y binaries to understand these like invisible structures. Yeah, and so now let's come to see like how binaries are, like our understanding of binaries is revolutionized by these modern surveys. So to talk about that, let's first get a sense about this physical scale of these binary stars. So here, the x-axis is the distance in astronomical units. So by definition, our Earth is at 1 AU. And here is the solar radius is about 10 to the minus 2 AU. And at the far right here is Alpha Centauri. It is the closest star to the sun. So this is about 10 to the 5 AU. So this is roughly the scale that we are talking about binary stars. And for binary stars, they can basically populate this entire range of these distance scale from 10 to the minus 2 all the way to 10 to the minus 5. Yeah. And by the way, these planets just put here just to have a feeling of the scale. But in fact, for the rest of the talk, we will not talk about planets that much. Yeah. So binaries basically can populate all the way in these distance, this separation range. Then how do we find or how do we identify these binary stars? So if binary stars, their separation are very, very close, then chances are very high that at some point they will eclipse each other. And in that case, you will see that even if you do not resolve them, you will see that the light curve actually change over time due to the eclipse. And that's why we call them eclipsing binaries. And in fact, they are probably the earliest binary that we know in human history, like probably back in like ancient Egypt days. Okay, and now with the time domain photometric surveys, we actually found a large number of eclipsing binaries right now, and partially thanks to some surveys specifically for planets like Kepler and TESS, and also some surveys for other kind of transient events like assassin and ZTF. Yeah, so eclipsing binaries right now have like much larger number than before. Okay, then if we move to larger separation, then at that time the eclipsing probability becomes very low. And then, but because their separation range actually corresponds to orbital periods about like within a few years. So in that case, within like our observation of like in a few years, we can actually see some change either in their radial velocities or in their astrometric positions. So in that case, we can still identify them as a spectroscopy or astrometric binaries. And for radial velocity binaries, then typically we need like time domain spectroscopy surveys, in particular Apogee and Sloan 5. Yeah. And when binaries get wider and wider, at that time, their orbital periods are very, very long. So for example, about 100 AU, they correspond to 1,000-year orbital period. So at that time, basically, we do not see any orbital motion anymore. And therefore, in that case, we'll probably just see them as a two-star resolved star, especially above this separation, and they move together on the sky. And I will talk about that, how we identify these white binaries in more detail later. Okay, so now with these surveys, we can identify much larger numbers of binaries and also populate much wider separation range. And that's actually critical for us to understand these binaries. And furthermore, because these surveys actually also provide us other critical information about stars. For example, for spectroscopy surveys, they give us metallicity and chemical abundances of stars. And also for astrometric survey, especially Gaia, it gives us kinematics of stars. And later, I will say that it actually also tells about the stellar age. And therefore, now with metallicity and stellar age, we can understand these binaries much more, like much better than what we did before. Okay, so now in this talk, I will first start with the lifetime of the main sequence contact binaries. And then later I will talk about the more general, like the comparison between closed binaries versus wide binaries. And in the end, the interplay between closed and wide binaries. Okay. So our main character here is the main sequence contact binaries. So main sequence contact binaries, they are main sequence stars, but they are in contact with each other. So they are very close to each other. So it's just like this picture shows. And so because they're already in contact with each other, it means that their separations are just a few solar radii. And their orbital periods are also very, very short, just like shorter than 1 day. But this separation is very weird because, so right now they're already in contact with each other, but this separation is weird because when they were still baby star, so when they were still pre-main sequence star, the size of the star is actually larger than their current separation. So it means that they must have a larger separation before so that they can fit in the size of their baby star. And then when they become a main sequence star, there can be some orbital migration so that the separation can become smaller and smaller and become the contact binary that we see today. Therefore, some orbital migration must happen so that they can shrink their orbit and become the contact binary. There are 3 mechanisms proposed for this kind of orbital migration and to form these contact binaries. So one is a pre-main sequence interaction. So pre-main sequence interaction means that when these stars were still baby stars, there are a lot of gas around them, and therefore they can shrink their orbit by like interacting with the surrounding gas and therefore become short period binaries. And the second scenario is the three-body interaction, in particular, Kozai-Lidov mechanism. So I always want to like imagine this interaction of three-body system like the love triangle of stars. So it strongly depends on how strong the configuration of these 3 stars. And that's actually very similar to love triangle. So for the first case, unstable triples, in this case, 3 stars are initially very close to each other. So they are equally strong. So in this case, they will have a very intense fight with each other. And at the end of that fight, most of the time, they will end up with a close binary, and they will just kick on the 3rd star out, away. And so in the end, the 2 stars will live happily afterwards, and then the 3rd star will just live alone for the rest of its life. Yeah. However, in this scenario, the close binary, this one, will not shrink the separation anymore. So typically, they will not become a contact binary afterwards. They will just stay this separation and stay that way for a very, very long time. So in this case, it's not what we are going to consider for the formation of contact binary. But the other case is very, very special. That's the stable hierarchical triple. So in this scenario, initially 2 stars are closer to each other, and you have a tertiary companion that's over there. And the cool thing is that this tertiary companion is not just sitting there without doing anything. It's actually playing an important role in the dynamics of the inner binary. And in fact, under some certain conditions, this tertiary companion can actually drive the inner binary to highly eccentric orbit. And that's the so-called Kozai-Lidov mechanism. And at that time, at that highly eccentric orbit, then the binary can get close, very close at some point. And at that time, the tidal friction can help them to shrink the orbit and become a contact binary like this. So in short, the tertiary companion actually helps the inner binary to shrink the orbit and become the contact binary. Therefore, that's a scenario that we are going to consider, the three-body interaction, in particular, Kozai-Lidov mechanism. And the third scenario is the magnetic braking. So in this case, the magnetic wind of the star can also help carry away the angular momentum of the binary system and therefore help to shrink the orbit. And in fact, the timescale of these 3 mechanisms are very, very different. So for pre-main sequence interaction, the timescale is very short. It's only like a few million years after the star formation. In the second scenario, the three-body interaction, the Kozai-Lidov mechanism, the timescale actually spans from like a few million years all the way to a few 100 million years. And it depends on the exact configuration of three-body system. And the third scenario, magnetic braking, is the slowest one. It typically takes like a few giga years to shrink the orbit. And so because the timescale is so different, therefore in principle, if we know the age of contact binaries, then we should be able to know like which mechanism is the most dominant one. However, the challenge is that the age of binaries is very, very difficult to measure. And therefore, at that time, it's still an unsolved problem, like which mechanism is the most dominant one for their formation. But now this picture changed with Gaia, because Gaia now provides us this galactic kinematics, and we can actually use galactic kinematics as a proxy for stellar ages. So the reason is because on average, older stars move faster. So the reason is because when stars just recently formed in the Milky Way disk, they will have very, very small velocities relative to the disk. But when stars get older and older, then they will interact with their surrounding environments. For example, passing stars, molecular clouds, spiral arms, and therefore, on average, the speed of velocity becomes larger and larger when they get older. So therefore, the galactic kinematics becomes a way for us to track their stellar age. And in particular, now Gaia basically measured the motion of stars for billions of stars. So now we can use this method with Gaia. So now in this plot, the x-axis is the velocity of the stars. So remember that for older stars, they will move faster. And remember that this velocity is just velocity of the entire system, like single star or binary system. It has nothing to do with orbital velocity. It's just like the velocity of the entire system, like binary system. Okay, so in each velocity beam, then we compute the contact binary fraction. So it means that for each velocity beam, then what's the fraction of stars in that velocity beam that are contact binaries? And we identify contact binaries by their eclipsing light curves. In the end, we found that this contact binary fraction increases from low velocity n to mid velocity and drops at a high velocity n. And so why is that the case? Why is there a dependence on this stellar age? This is because we are basically seeing the lifetime of these contact binaries. So at the small velocity here, number 1 here, is when these binaries were still wildly separated, and therefore we do not identify them as a contact binary. But after a while, number 2 here, because they now have enough sufficient time to finish their orbital migration, and therefore now they show up as a contact binary now, because they now are very close to each other. And interestingly, there's a drop at the high velocity n, and it is because we believe that they are merged. So now, because they merge, and therefore they do not show up as a contact binaries anymore, and just a single star, and therefore we do not see them in these old stellar populations. So basically, with this kinematics method, we can see the lifetime of these contact binaries. And after exploring these parameter space, we found that their formation time is about 0.6 to 3 gigayears, and then they merge within 10 gigayears.
So this time scale is more consistent with the third scenario, the magnetic braking?
Yes, that's what we are definitely, yes, that's the next slide, yes. Yeah, and one last thing is that, so here you can see the red bars. So the red bars is from our very simple lifetime model. So in this lifetime model, we say that all contact binaries are formed at age of 1 gigayear, and they merge at 10 gigayears. And you can see that you actually can, with this very, very simple like 2-parameter models, you can actually describe these overall observational results very well.
For the Kozai-Lidov mechanism, another indication would be that it's part of a triple system, not just a contact binary. Can you use the latest Gaia data to measure the fraction of contact binaries that are in triple systems?
Oh, that's a great question. So in fact, we did that, and that's what we will come back to that later. And with Gaia, we can only prove very wide separation because that's limited by the resolution. Yeah, but also there are some people use spectroscopy survey to see if these contact binaries are in triples with like closer tertiary companion. And originally they found this fraction very, very high. So basically the conclusion is that for short period binaries like below 3 days, almost like 90-ish% of them are coming from have a tertiary companion. And that's actually why people like the Kozai-Lidov mechanism a lot, because that can explain why they have a tertiary and why they have this short separation for the inner binary. There's a lot of big debate about that afterwards, because for Kozai-Lidov mechanism to work, you actually need mutual inclination between the inner binary and outer tertiary. But there's a later work by Bolkovich, and they can actually use intrinsic timing variation to constrain this mutual inclination. And the conclusion is that they see a peak corresponding to the Kozai-Lidov mechanism, but they also see a lot of triple systems that are coplanar, where the Kozai-Lidov mechanism is not effective. So it's still under debate, what's the role of Kozai-Lidov mechanism playing in this short period binary and these triples. But it's still under debate. But for my work, we will from a different standpoint. We would look into the age dependence. So basically, as CL mentioned, so this time scale of about 1 giga-year formation time is definitely too long for prime sequence interaction and also too long for three-body interaction alone. And therefore, this time scale seems to be most consistent with magnetic braking. And they suppose that the magnetic braking probably dominates this formation of this contact binary, at least for the formation time. But it doesn't completely rule out the first two scenarios. So one possibility is that maybe the first two scenarios help them to move somewhat close separation, but not very close. And the magnetic braking help them to finish the last mile to become a contact binary. That's also possible. Yeah.
Do you have a sense of, so suppose that is the case where the first two, bring it somewhat in and then the magnetic braking. Do you have a sense of what the different length scales would be for that?
Yeah, that's a great point. So we believe that for Kozai-Lidov mechanism, that will probably happen after about separation about or orbital period about 5 days to 10 days. And the reason is because at that time it's most likely where they will get tidally circularized. And therefore at that time the Kozai-Lidov mechanism become less effective. So yes, so one possibility is to look for the time, so basically apply the same thing, the age dependence, for a slightly longer periods of the sample. So our sample right now is within, most of them have a period within 1 day. Yeah, but probably a good question to ask is to what about longer period, about 5 days? And in that case, we may see the some feature about this three-body interaction. Okay, so this is about the formation time. Then how about the merger time? So in our result, we see that these contact binaries disappear in all stellar populations. And that probably implies that this merger of contact binaries do happen in the Milky Way and also in these contact binaries. And in fact, there's currently one known event and the only one event observed in the Milky Way. That's this case. So this case, so here is basically the observation time from 2001 all the way to 2010. And its explosion happens in about 2008. And so there's a very beautiful explosion event. And you can see there's some wiggles before the explosion. And in fact, if you zoom in the wiggle, the wiggle is actually a contact binary curve. So it's a very special case where we see the explosion and we see the progenitor contact binary. And in fact, we also see the orbital period decayed before the explosion. So it's a very, very special case. And in fact, its light curve evolution actually looks very similar to a class of transient events called luminous red novae. And actually, there's quite a lot of discussion about whether or not all these luminous red novae are coming from these contact binary mergers. So yeah, so to connect these our results and with these contact binary mergers, we have a few works in progress. For example, we are currently looking for some contact binaries that are on the way to merge. So the way to find them is to find contact binaries that have the rapid period change. And we actually have a few candidates. That's pretty interesting. And the other way is to find the merger remnants of these contact binaries. So presumably, if they merge, they may become a blue straggler with very fast rotation. And in that case, we may look for those features with blue structure that have super fast rotation. That's the goal. Yeah, and if you're interested in it, let me know, and I'm very happy to talk about them in more detail. Okay, so that's the first part. That's about the lifetime of main sequence contact binaries. But now let's move to a more general case, like what exactly is closed binaries and wide binaries? So is there any clear definition for them, or it's just an arbitrary like words? So in fact, in literature, most of the time, when we say closed binary and wide binaries, they're often arbitrary. So in papers, there can be like ultra wide binaries, all different kind of words. But in fact, there is still some physically motivated way to think about them. So for example, there are different formation mechanisms responsible for different separation, like the disk fragmentation, where if you have a star and you have a protostellar disk, and when the disk, especially when the disk is massive enough, then the disk can fragment and form another companion star and become a closed binary. And in that case, the closed binary is limited by the scale of the disk. Yeah, and there's also some other mechanism for wide binary stars is, for example, the turbulent core fragmentation, which is basically the fragmentation of the molecular cloud's core, and that can also contribute to wide binaries. And there are also a lot of other mechanisms to form binaries at different separations. But yes, there's a physically motivated formation mechanism to motivate this definition between closed and wide binaries. However, observationally, for example, separation distribution, we actually do not see any obvious feature to see, oh, if there is closed binary or another bimodality for wide binaries. No. In fact, we see a pretty smooth distribution for separation distribution. So then the question is there any very clear distinction between closed and wide binaries? And the answer is yes. So we will start from metallicity dependence and then their eccentricity distribution. So for metallicity dependence, people have looked into this metallicity dependence of closed binary fraction, like in the last decade. And the conclusion right now is that, yes, there's a strong metallicity dependence, and the closed binary fraction increases with decreasing metallicity. So in this plot, the x-axis is metallicity, is iron abundance normalized by the hydrogen, and is normalized so that the value 0 is solar metallicity. And it is in log scale, so -1 means it's 10% of solar metallicity. And you can see that at lower metallicity and the closed binary fraction on the y-axis is much larger. And people think that it supports that these closed binaries are formed from disk fragmentation, where disk is easier to fragment that lower metallicity case. And interestingly, this anti-correlation between metallicity and what closed binary fraction somehow disappears around 100 AU. So then my question is, so how about the metallicity dependence of wide binary fraction? About 1,000 to 10,000 AU. So now,
is there any metallicity variation in the two stars themselves, or
you mean that between two stars?
So for both stars in the binary, what's the scatter in their metallicity?
Yeah, that's actually a great point. So yes, people do look into that as well, and that's actually have very interesting and actually important implication, especially for something called chemical tagging. So basically, the idea is if two stars form together, do they have the same chemical abundances? So people look into that in using high spectroscopic resolution, and especially I think a few work by Hsiang-Chih group. So basically, the major high precision chemical abundance is not just about iron. So they basically measure 10-ish chemical abundances. And what they found is that most of them have exactly the same chemical abundances within their uncertain errors. There are still a few cases that have a little bit different chemical abundances. And some people would argue that, oh, maybe one of the stars accretes some planets, and therefore you get a different chemical abundances. But otherwise, I know people think that if these binaries are both formed together, and they do have very close, very similar chemical abundances. And people use that to argue that yes, so chemical tagging can work, which means that you can use chemical abundances to group which star were formed together. Yeah. Okay, so my work is I want to ask that what is the metallicity dependence for binaries at 1,000 to 10,000 AU? So at this separation, these binaries basically are resolved. And then how do we identify them as binaries? So here's an example. So typically it's an image. So by image itself, it's very difficult to. It's actually very interesting that it looks noisier on the screen here. Okay, but it's pretty difficult to identify which two stars are in a binary just based on the image itself. But now, because Gaia measured the proper motion and parallaxes of the stars, so that actually helps us a lot to identify these binaries, because at these wide separations, the orbital velocity are so small, so that basically they have you can treat them as like zero relative velocity for the binary, and therefore these two stars would just like move together on the sky. Okay, so now let's add the Gaia's proper motion data here. You can actually see that, wow, actually with these arrows, these proper motions, you start to see some promising moving candidates. So for example, this one, these two is very just like move together. It looks like a perfect comoving pair. And the other one I will pick is from this one. This one also looks very similar. But then if we add another information, which is parallax, that is basically the distance of the star, then we can confirm that actually this one is a Y binary and the other one is this one. So it's actually not that obvious directly from the if we only have proper motion. And you may ask, how about this one? And it turns out that one has a slightly different distance compared to these two. So it may not be a component of this system. Okay, so basically we apply this method and to search these Y binaries, and because we have the proper motion and the information of distance, the contamination is actually pretty low from chance alignment pairs. I think it's like about a 1% level. Yeah, and then we can combine with other spectroscopy survey like MOS to investigate the Y binary fraction as a function of metallicity. So here we see that the Y binary fraction peaks around solar metallicity and decreases towards both low and high metallicity ends. So first thing is that, wow, it's very, very different from what we saw in close binary fraction. So it basically means that they are coming from a different formation mechanisms. But the second thing is that, but why is there such a weird metallicity dependence? It's a non-monotonic metallicity dependence. So we think there are three possibilities. For example, one is the purple one. It basically means that these low metallicity and their metallicities are lower and they are on average older stars. And therefore, maybe the reason we see a smaller Y binary fraction is because these older stars have a more denser formation environments. And because a denser formation environment will tend to disrupt the Y binary, and that may be the reason we see a smaller Y binary fraction at low metallicity end. And for the blue part, the high metallicity end, this actually looks a little bit like the close binary the metallicity dependence of close binary fraction. So one possibility is that maybe these Y binary are coming from the compact three-body interaction, and therefore once they kick one star out, but if that star is not completely ejected, then they will become a Y companions. And because they are coming from the compact triples, so they will follow a similar metallicity dependence as the close binaries. And the other scenario is a radial migration scenario of the galactic orbits. So in this case, because in our study, the sample is a very local sample. So it's like we think about a few 100 parsec from the sun. And so most of the stars are thin disk stars. But for these very high metallicity stars and very low metallicity stars, they are probably formed somewhere else in the Milky Way, and they have somehow radial migrate to the solar neighborhood. And therefore, the fact that we see a different wide binary fraction may be related to their formation environments at different locations in the Milky Way. Yeah, so there are three possibilities for this kind of weird non-monotonic metallicity dependence. And we actually follow up this further. So before we only focus on thin disk stars, but now in this study, we also include thick disk stars and also halo star. So especially for the blue point, that's for the thick disk star, we actually also see the decreasing wide binary fraction at low metallicity end. And we want to do this because for thick disk stars, we actually expect them to have less effect from radial migration. And therefore, the fact that we can see this effect basically means that it must be something that is common for thin disk and thick disk stars. And therefore, we conclude that at a low metallicity end is basically due to these formation environments at different time instead of that radial migration. But for the high metallicity end, it can still be that two scenarios, the compact triples or the radial migration. Because for this high metallicity end, the thick disk and halo sample has very little constraining power at that point. So therefore, for this metallicity dependence, we know that these closed and wide binaries are very different, and therefore they are likely coming from the different formation mechanisms. And the other way to understand these closed binaries and wide binaries is through the eccentricity. And that's actually what I've been focusing on in the past year. So I'm focused on how to develop a method to measure the eccentricity of wide binaries. And the reason is because eccentricity is difficult to measure for long period wide binaries. So traditionally, if we want to measure the eccentricity of a closed binary, we want to track its binary orbits over its entire period. So for example, we want to track its radial velocity, and then after we collect the data for the entire period, then we can solve for its eccentricity. However, for binaries with separation larger than 100 AU, their orbital periods are longer than 1,000 years. Then there's basically no way for us to track their orbital period. And does that mean that we cannot measure the eccentricity at all? And the answer is that we can, and we can actually constrain their eccentricity distribution pretty well. And the idea is actually pretty simple. So here in this plot, there are like two binary orbits. One is a circular one, and the other one is an eccentric binary orbit. And the color code shows something called VR angle. So this is the angle between V vector and R vector. So V vector is the relative velocity vector, and R vector is separation vector. And so for a circular phase on circular orbit, this angle, VR angle, is always 90 degrees. But for an eccentric orbit, this angle is not 90 degrees in general, and it actually depends on its underlying eccentricity and also orbital phase. Therefore, from this, we can kind of feel that this angle carries the information about the eccentricity. But in reality, binaries have all kind of different orientation, and also there's some projection effect. So can this method still work for that in reality? So to answer that, here in this plot, we simulate binaries with all random orientation. And also the x-axis is the observed VR angle. So by observed VR angle, it means that it's the angle between projected V vector on the sky and also projected separation vector on the sky. So there's an observed quantity that takes the projection effect into account. Okay, so now let's take a look at the blue case, where all binaries have circular orbits. So remember that if they are phased on circular orbits, then basically you will see a delta function at 90 degrees. But now, because this orientation effect and projection effect, we still see a strong peak at 90 degrees, but now with a very long tail towards 0 and 180 degrees. And now let's move to the second example. That's where all binaries have eccentricity of 0.8. Then in that case, you will see the peak about 40 degrees.
Sorry, I think I just missed this. So how are you populating the histogram, right? The angle changes over the orbit. So you're just randomly sampling from different points in the orbit for a population and okay.
Yeah, that's right. So in this simulation, we have like random orientation, but also random orbital phase. Yeah. Okay, so basically you can see that for more eccentric binary, then you will have this peak closer to 0 and 180 degrees. Okay, and there's also a few other cases. For example, let me explain this red one. For the red one is the case when the eccentricity distribution is proportional to eccentricity itself. And it's a very special case, which is called thermal eccentricity distribution. And in this case, that actually gives you a flat VR angle distribution. So therefore, this is basically telling us that even we have this random binary orientation and also the projection effect, we can still have very, very different VR angles distribution from different eccentricity distribution. So basically, if we can observe a VR angle distribution, then we can infer what's underlying eccentricity. And one powerful thing is that this method only depends on this angle. So it actually doesn't depend anything about the mass and the distance of the binary system. So that's actually makes it very, very powerful and useful. So now let's move to the observational results. So here, for observe Y binary results, Y binary, the R vector is just a separation vector connecting to two stars. And the V vector, the relative velocity vector, basically have the same direction as a proper motion difference. Therefore, we just need to measure the angle between VR angle, and then we can get the VR angle distribution. And one amazing thing is that Gaia's precision is actually can measure this VR angle for binary separation out to 10 to the 4 AU, where the orbital period is like 1 million years. So there's basically no way to use a traditional method to get eccentricity for these super wide binary. But now with Gaia, yes, we can actually constrain the eccentricity distribution. So here is a observational result. So for the blue one is for the closed binary between 10 to 100 AU. So you can see that there's an enhanced number around 90 degrees, but also a reduced number about 0 and 180. So that's actually looks pretty similar to what we expect from uniform eccentricity distribution, which is the black histogram in the background. And when we move to larger separation, like 100 to 1000 AU, we can actually see that this separation, this VR angle distribution becomes very flat, indicating the thermal eccentricity distribution.
Do you not have distance to get that separation in AU?
Sorry, you mean here?
Yeah, be able to put them into different boxes. Did that not require the distance?
Yes, so they are basically different in binary separations. Yeah.
But you mentioned you don't need distance to use this technique, but at the same time, you do need distance to be able to bend them.
Yeah, so that's correct. Yeah, so we don't need distance to get the angle.
Yes.
But if we want to understand the property, like in terms of binary separation, then in that part we need distance.
It's a wide binary, you need distance.
Yeah. So yes, for this part we need distance to bring the data. That's correct. Okay, and for very wide separation, 1000 to 10,000 AU, the cool thing is that we're actually seeing a pile up of number of wide binaries at 0 and 100 degrees. So it basically indicates that there are some highly eccentric wide binaries in this separation range. And if we model this VR angle distribution using a power law eccentricity distribution, then we can map their eccentricity distribution on the y-axis as a function of binary separation. And so the y-axis is a power law index for that eccentricity distribution. So 0 means that it's a uniform eccentricity distribution, and 1 means it's a thermal eccentricity distribution. So in this way, we can see that the eccentricity distribution changed from uniform all the way to super thermal eccentricity distribution at larger separation. And what we are looking here is basically the transition from closed binary formation to wide binary formation. So a small separation, they are dominated by closed binary formation, and therefore they have more interaction with the disk, and or even maybe some of them are formed from the disk fragmentation. And that causes this uniform eccentricity distribution. And the Y separation, it indicates there are some formations that contribute these highly eccentric binaries. There are several possible mechanisms, like co-fragmentation can also give these highly eccentric binaries. And actually CR and I, we are also looking into a scenario where the random pairing in star forming region can also give you a highly eccentric distribution. And also one possibility is whether or not this effect can, this eccentricity can be due to the galactic tides. And in fact, the recent paper by Chris, he basically looked into it, and the conclusions is that galactic tide alone cannot explain this superthermal eccentricity description. So basically, we need an initial superthermal eccentricity, we need an initial superthermal eccentricity distribution to get this. Yeah, so basically, in the end, this must be coming from the binary formation. Therefore, right now we have the metallicity and dependence and eccentricity distribution information, and this so this basically concludes that binary below 100 AU are dominated by this closed binary formation, and above 1000 AU are Y binaries.
Yeah, so this is very far outside my field, so this may be a very silly question, but how do you actually identify the binaries? Is it from the parallax? And then are you just not worried that there are selection effects for?
So do you have any particular selection effect in mind, or?
I don't know.
Or you mean like contamination? Like
very naively, I would imagine it would be easier to see binaries that are highly, if like the semi-major axis is large, it'd be easier to see binaries that are highly eccentric because they're like nearer to this.
That's exactly right. So yes, so particularly for that VR angle method, right? So yes, there's actually several selection effect we need to be careful about. So for example, you could say that for high eccentric orbit, then you actually stay longer at larger separation. So that's one thing. And also because for an eccentric orbit, larger separations, then you have smaller orbital velocity. And at that time, you may not be able to measure a VR angle because the velocity is too small. So that's another selection effect. So yes, there are several selection effects. So yes, in our paper, we need to be quite careful about that. And so in the end, we need to select a sample within 200 parsecs. So it's a pretty close sample, so that we need to make sure that we can measure this VR angle correctly and also avoid selection effect. But that's a very good point. Okay, so basically here we have this conclusion, but now the next part is that what is about the interplay between closed and wide binaries? Because now everything looks very, sounds very good. Like, okay, below 100 AU is closed binary, above 1000 AU is wide binary. But is there any okay, and also the transition between about 100 to 1000 AU. But is there any exception, like for example, closed binary, but somehow get to wide binaries? Is that possible? And in fact, we found that the answer is yes. So there's a very special population called twin binaries. So twin binaries means that they have almost equal mass components. And people have found that in closed binary population, there's an excess of equal mass binary. So here is an example of the mass ratio distribution. So you can see that from 0 to 1 is pretty smooth, but there's a huge spike, almost 1. And this is a model plot, but in reality, it's actually pretty similar. So there's a huge spike for equal mass binaries. And also this spike is so narrow, it's also about 5% narrow. So it's unlikely to be gravitational effects, because for gravity, 0.9, mass ratio of 0.9 and 0.95 basically are very similar. So it seems that it must be some hydrodynamical effects. So for example, people think it could be the competitive accretion in a circumbinary disk. So it basically means that you have an inner binary and you have a disk surrounding it, and somehow the lower mass components somehow have a higher accretion rate. And therefore, this lower mass component can catch up the higher mass component and become an equal mass system. And this also explains why these twin binaries are more common in closed binaries, because you have to be within smaller than a circumbinary disk. But the problem is that with Gaia data, there's actually twin wide binaries have been found. And they actually can be seen all the way out to several thousand AU. So here's the plot. So the y-axis is the delta G. Delta G is the G-band magnitude difference between two Y binaries, and the sign is just arbitrary. And let's look at the right panel, which is the the physical separation. So you can see an enhanced spike about 0, which is twin Y binaries. And that's actually can be seen all the way to several thousand AU. And this is, so basically the selection effect have been excluded. So it seems that there are a real twin Y binary population. Does that fit well with our previous picture that they have to be located within a certain binary disk? So there's a hypothesis basically saying that these twin binaries basically were initially born as small separations, so they still can be within a certain binary disk, but somehow their orbit was widened by some unknown subsequent interaction. And if that's the case, it means that they must have a highly eccentric orbit. And therefore, my method can basically directly test this and see if they are eccentric. And in fact, the answer is yes. These twin Y binaries are extremely eccentric. So in this plot is the VR angle of these twin Y binaries, this blue one, and compared to the non-twin, you can see there are a lot of these twin Y binaries with angle close to 0 and 180. And with our model, we actually can constrain that this eccentricity of twin Y binaries are actually between 0.94 all the way to 0.99-ish. I call that 0.99-ish is because basically it's our precision limit. So it could be a lower limit. And here it actually shows how a 0.99 orbit, face-on orbit looks like. And if you look very, very close, there's actually a red dot here that actually indicates a pericenter passage. So it's a very, very eccentric case. And with this information, we actually found that their pericenter is within 10 AU. And that actually agree with the hypothesis that they are originally formed from closed binaries with a certain binary disk. The remaining puzzle is, so what makes them eccentric? So for example, is that three-body interaction? It seems not, because we do not find these twin binaries to have unresolved companion. Is this because there's some velocity kick during star formation that makes them very eccentric? Probably also not, because there's just no known velocity kick source in star formation theory. Or is any interaction between a certain binary disk? This is probably something I'm currently thinking about, because for these equal mass twin binaries, they probably likely have a very massive certain binary disk. So maybe that somehow makes them highly eccentric during some condition, certain situations. But if you have any idea about that, please let me know. I really need your help.
Are they contact binaries?
So yes, so actually contact binaries, some of them are also twin binaries, that's true. So for very, very short period n, yes, people also see these excess of twin equal mass binaries. Okay, so that part is about twin binaries where they are formed from closed binary, but we now see them in Y binaries. What about other interplay between closed binary and Y binary? So we don't talk about them, closed and Y here, but how about triple system and quadruple system, like these two? So the ultimate goal is so can we use closed binary and Y binaries to understand these triples and higher order systems? So the other way to ask this is, can we treat these closed binary formation and Y binary formation as an independent process? So in that case, the Y triples is just basically having a closed binary formation and then Y binary formation independently. So to test these scenario, we basically ask two questions. The first one is, are closed binaries more likely to have a Y companion, so closed binary here? Does it more likely to have another Y companion compared to the field star? And the second question is, if we have a closed binary and we find its Y companion, is the Y companion more likely to be another closed binary? So if closed binary and Y binary formation are completely independent, then the answer would be no to both these two questions compared to the field stars. But we found that in fact, both answers are yes. And this actually I answer to Jim's earlier question. So what about the Y companion about closed binary? So indeed, we found that the closed binary are about a factor of 3 higher chance to have a Y companion. And for the second case, for the companion of a closed binary, we found the chance is 7 times higher to be another closed binary compared to the field closed binary fraction. So why is that the case? So in both studies, the inner separation is only about 0.01 AU. So they are basically contact binaries. And the outer separation are 10 to the 3 to 10 to the 4 AU. And these super extreme separation ratios actually is not that possible for cosine lead-off mechanism to be effective. Then why can these closed and Y binaries correlated? So one possibility is that maybe the Y companion somehow promote closed binary formation. So for example, if you have Y companion and you have an inner star with a disk, maybe the Y companion somehow make the disk easier to fragment. Or the other possibility is that maybe they are formed in a coherent way, or even the form of spatial, they are formed from a spatial channel. So for example, one scenario is that maybe they are formed from the compact triple interaction. So remember that we originally mentioned this compact triple, and once they have chaotic interaction, sometimes they will kick the star out. But if the star is not completely ejected, then they will become a Y companion. Then in that case, you will form a closed binary and with a Y companion correlatively. So in other words, even so we now look into a lot into closed and Y binaries, but it seems that triples and quadruples, they are still have a lot of unsolved problems for them. So I think that's basically my conclusion today. So basically we look into the lifetime of these closed binaries, and we use that to understand their orbital migration and their merger fate. And also we use the metallicity dependence and eccentricity distribution, so that now we know the clear distinction between closed binary and Y binaries. And in the end, we show that there's still pretty complex interaction between closed and Y binaries, like the twin Y binaries, where they are formed from a clean closed separation and ejected to larger separation, and also the complex correlation between closed and Y binaries in triple and quadruple systems. So hopefully with the upcoming data and especially Gaia DR3, we can solve these questions very soon. Yeah, that's all I have, and I'm happy to take questions.
Do you ever see Y triples?
Yes. So yes, we actually see Y triples, and I didn't have any paper on that, but I actually found that very interesting. And so the interesting thing is that I found that these Y triples tend to be younger, so kinematically younger. So one possibility is that these Y triples may be something that currently disrupting, and therefore some of them are leaving away, and therefore we will only catch them at a younger age. Yeah, so yes, we do see these Y triples, but the numbers are much fewer compared to Y binaries, these populations.
So I don't understand how the VR angle method doesn't care about the projection effects.
So basically it means that we need to include a projection effect in our model. So you can imagine that. So we still care about projection effects. So for example, or orientation. So for example, if that all binaries have some specific orientation, then in fact that will affect our results. We actually have some tests about like how well like randomly oriented, how random are they? And right now it seems that they are very random. So for example, we can check whether they align relative to the galactic coordinates, and they pretty much very randomly oriented. Yeah, but yes, we need to include that in our model to infer these eccentricity distribution from VR angle. Yeah.
So on the, I think it was a plot with Gaia data, and you showed first the motions, and then you showed the distances, and there was the red herring in that. So the one that looked like it would be a binary, but then wasn't a binary, because you said they were different distances. Are they very different distances or, sorry, I don't remember the slide number. Yeah,
You mean this one?
yeah, the one down there. And so
Yeah.
that one ends up not being part of the, or it ends up being, that's not a triple. My question is that a triple or is that actually really far away?
Okay, so the answer is this is actually one of the 2+2 system. So it's actually very, very interesting. So this one is actually short period binary. This was the other short period binary. I hope I can find a plot that I skip if I can find it. But yeah, so that's actually a short period 2+2 system. Let me try to find it. Okay, here you go. Yeah, so that's actually this system. So it's actually 2+2, and the other one is not that obvious here. So that's this one. Yeah. So if this turns out to be the companion, then it becomes 2+2+1 system. So that would be super, super cool. And so I hope that in future Gaia release, they will update this, improve the quality of this companion, because right now I think it's a little bit too close, and therefore in the previous Gaia release, the noise is pretty large, and you can see that that star is actually pretty faint. So I hope that in the future Gaia release, they may improve the quality, and maybe we will see that it has a consistent distance, and then it can become a super cool 2+2+1 system. Yeah, and I don't know whether or not there's another correlation, like 2+2 system tend to have more another companion. We don't know, but I think it's pretty cool. Yeah.
There's also sort of nature versus nurture question, which is for these very wide binaries, 10⁴, 10⁵ AU, getting to a parsec, and the initial birth environment was perhaps a cluster, or there was a lot of molecular gas around within a parsec. And so for the first million years, you might imagine the orbital evolution was quite rapid because you were part of a cluster that eventually dispersed over the next giga-year and left behind some wide binaries. So, but how do you separate very rapid dynamical evolution in sort of a cluster environment that occurs very early on in the stellar lifetime versus quasi, lead-out mechanism or other things where now you just have a triple system that's evolving by itself in the potential? And where does that boundary occur, and how do you know how much it?
Yeah, that's actually very difficult. So there's a lot of things can happen, especially in this separation range. So especially beyond 10⁴ AU, you can have passing star, you can have molecular clouds, you can have spiral arms, you can have galactic tides that can all affect binary beyond 10⁴ AU. And about 10⁵ to 10⁴ AU, the cluster is actually also something relevant. So actually in our metallicity dependence, that's something we want to argue, is because if it is in a strong, very dense cluster environment, they'll probably reduce the formation of these wide binaries. But another thing is that also there's some simulation paper that show that binaries can also form from cluster dissolution. That's also a very special case where if a cluster, when they dissolve in the Milky Way, then two stars can actually form together. And in that case, then you can also form wide binaries. And how do we distinguish them? So one cool thing is that for that simulation paper, they actually predict a thermal eccentricity distribution for these wide binaries. So it means that if that cluster dissolution scenario is a dominant binary formation channel here, then we will expect them to see a thermal eccentricity distribution. But we didn't. So it seems to suggest that we need to something else to, in addition to that cluster dissolution, to fill in this. So in short, is that basically and also another thing I want to add is that for very wide separation, another thing to explore these nature versus nurture methods to look into the age dependence. Yeah, so because for passing star, those effects basically they can accumulate with stellar age. So you will see a stronger age at older stars. Yeah, and actually some people look that into, for example, separation distribution. They also see some trend that there's some break in separation distribution out about 10⁴ AU. Yeah, so that can support them that it's probably some age-related effect. Yeah, so that's probably how we like address this problem. But indeed, it's a difficult question.
Other questions online? Oh, okay. So let's thank Hsiang-Chih again. Thank you very much.